Hello, I'm Josh Walters, and this is Akshay Sharma. We're software engineers at Yahoo working on the user traffic data pipeline, which processes about 200 billion records per day. I'm going to be talking about data partitioning and why we do it at Yahoo. This data that we generate is queried many times by analysts inside Yahoo, and so we have to optimize for their use cases. Partitioning is one way we can get a massive boost in query speed and grid utilization decreases. So, simple example over partitioning, I'm sure everybody here knows it, but if you have a school database or a customer database you might want to partition on regions. School, you might want to partition by class to group data logically together into sets that might be hit together. So what is deep partitioning? So deep partitioning is really nested levels of partitioning. In this case, we do everything on the grid, so for us, nested partitioning is levels of partitions. You want to go as deep as physically possible if you're doing very, very large-scale data to enable very fine-grained access controls for your analysts so they can hit the smallest subset of data possible. This can have massive, massive gains for grid utilization. So, simple example, if you have a partition structure, state, last name, first name, and you want to find Bilbo Baggins from the Shire, it's very easy to find him given this partition structure. If you don't know completely what you want to find, you can just pop in standard Unix file path globs and you'll still get the data that you're looking for. So it works for all the use cases that you could normally think of using this for. So there are a few problems with deep data partitioning, specifically around cardinality. As you increase data partitions, you can have a huge explosion in part files and the number of partitions because it's a multiplicative process. Also, as you greatly increase the number of partitions, you can start dropping in data partition locality. A lot of your different reducer nodes or partitioner nodes will have the data spread out more, so the data is not as clustered and your compression rates end up dropping. We have a few solutions for that, and Akshay is going to go over our current solutions.
All right, so probably should go here. Okay, so let's say you have n machines trying to partition the data. The data is essentially random, so each machine could get data for any partition. Let's also say for simplicity's sake that when a machine writes out to a partition, it will write out one file, although in practice it could be more. So the naive way you could think about doing this is each machine write to every single partition. So if you have n machines and j partitions, there'll be n times j, which is obviously very bad. So you wouldn't want to do that. So what can we do? So the idea is to group the data for partitions so that a machine handles one of them. But what if a partition is too small or too large for a particular machine? If it's too small, it means that a machine can handle more than one. If it's too large, it means it has to work together with other machines to write out that partition. Okay, so, how do you know how large a partition is going to be before you get here? So the trick is you have to actually compute this before you get here. Now, while that seems wasteful, it's not actually that bad because you do deep partitioning at the end of your processing more often than not. So you actually control the generation of the input to this partitioning stage. So while you're generating that input, you could think about computing the metrics at the same time. Now, if the metrics computation is intensive, you could also sample because that big data sampling provides a very good approximation for the sizes of partitions. Okay, so let's go through an example of what we do here. So let's say we use count as an approximation for how big a partition is going to be. Count is actually not that good, but for the discussion purposes here, let's just use count. If we have 10,000 events and 1,000 of them belong to Shire, Baggins, Bilbo, that means that Shire, Baggins, Bilbo would need 10% of the machines to handle that load. So, given these given the sizes of each partition, that we can then divide up the. Oh. Oops. Yes. Okay. So given we have these percentages, we can easily divide up the machines accordingly. Now, there are many strategies to account for here. You can't just simply divide up the percentages with machines. For example, let's say you have a lot of partitions that are 2 or 3 machines worth of sizes. If you divide them accordingly, they may be underutilized. So you would actually have to share them, share the adjacent partition with this particular one that's underutilized. So even given that the worst case is when each partition is written to by 2 machines, the worst case is now n plus j minus 1, which is still loads better than before. Okay, so that's all we have. There are many other issues to consider here. We've been optimizing for the number of files generated. You could optimize for other things such as compression, locality, or even speed of processing, or a combination of all of the two. So yeah, we have way more to talk about this here. So come find us after the talk, and we can explain more. Thanks.